Okay, so I will start by talking about the midterm exams. Okay, so I guess just the first midterm exam. You guys can see my screen, right? Okay, so so we're gonna have the exam on Wednesday, April 22, and so that's next week, and we are going to so the exam's open book, but no collaboration allowed. You can't be talking to each other, and this is what I've decided to have a live exam. Okay, and so the way the live exam is going to work, I'm going to have one exam from 10 a.m. to 11:10 a.m. Okay, I'm assuming that's going to be okay with most of you guys. All right, so I know our class meets from 11 to noon, but just for the exam, you're going to have to get up an hour earlier and take the exam from 10 to 11. Or if you live in a distance time zone and you're watching the video for this, okay, I will have a second exam from 10 p.m. to 11 p.m. And these are both California time, so you got to figure out what time it is for you in your time zone. But I'm hoping between having one at 10 a.m. and having one at 10 p.m., something's got to work here. Okay, something's got to work. So so you take whichever exam you would prefer. I'm going to have slightly different versions of these things, and I'm going to proctor them via Zoom. So you're going to log into Zoom. Just like you are now, or for those of you who are live now, but you'll turn your webcams on, keep your microphones muted, and that's how we'll do the that's how we're going to proctor it. Okay, okay, is that okay? Are there questions there? Are there any issues there? Does somebody have like a class from 10 a.m. to, well, nobody's going to have a class from 10 p.m. to 11 p.m. California time. So one of these times has to work for you. Okay. So we're going to do that. Okay. The exams are going to be pen and paper exams via Gradescope. Okay. And so the way this is going to work is there's going to be like this little, there's going to be a link on CCLE that links you to Gradescope. You click that, and there will be a PDF of the exam, and the exam, the PDF of the exam will be 5 pages long. Okay, and you can choose to print that out. You don't have to. Okay. But I'm going to make a PDF of it, and you're going to answer each question on a piece of paper. Okay, so the exam is going to be 5 problems, and so you're going to need 5 sheets of paper. Okay, and you're going to do each problem on 1 page. Okay, so just one side, one problem per page, and all of the work for one problem has to fit on 1 page. Okay, so don't write on the back. I'm hoping the exam, like, I'm trying to write problems that can definitely be done on 1 page, and so so yeah, one problem per page. Okay, so we have a question. The exam is on iPad, or can it be on, or can it be on the iPad or actual paper? Yeah, I think. I don't know. I'm not familiar. I haven't used Gradescope before. This is going to be my first time. So I think you can do it on the iPad as long as you can save your PDF and upload your PDF back to Gradescope. Okay, because that's how it's going to work. Is you're going to you answer your questions, and then once you're satisfied with your answers, then you have to either scan it. You have to turn it back into a PDF somehow. Okay, so if you have an iPad, and you can write on it. I think it's going to work. You just save it as a PDF, and then you upload that PDF back to Gradescope. Okay, you got to make sure your answers are visible. And so what I've done is I've created a practice, just like a practice. It's not even it's not a practice test. It's more like a practice using Gradescope assignment. Okay, so it's like the question is like, what's the integral of sine? And I also ask a question like, what are your goals for the next 3 months? Okay, I know we're all living in social distancing and quarantine, but you know, that doesn't mean we should give up on our goals. So you know, anyway, you know, how seriously you want to take the questions I've asked, you know, up to you. But the idea is, I just want you to try. You have to be able to scan a multiple page PDF document, and you have to be able to upload that onto Gradescope. Okay, finish that by Monday, and I'm going to go through and I'll just check to see if and if there's an issue, I will let you know that there was an issue with your submission sometime on Tuesday, and hopefully you can figure out how to fix it. So if you've never used, so some of you actually have access to a scanner, like you have a real scanner, which you know, great, you can use that. If you don't, you can probably find like a scanner app for your phone where you just where you take pictures. You know, you point it down at your piece of paper and you point it and you take a picture. On Android, you can use Google Drive. Google Drive has an automatic scanning feature, and it automatically uploads to Google Drive, which I really think is great. If you don't have an Android phone, you can use the Notes app on your iPhone. There's other apps. There's like Microsoft Office Lens, which is also pretty good. There's like Cam Scanner and stuff. And when you scan them, please take the time to like crop them and you know, or at least just make it fit the piece of paper. Okay, well, okay. And you're going to upload that back to Gradescope, and that's how we're going to try to do the exam. Okay. Can you use the computer to look at the notes? And someone asked, is it open internet? Open. Okay. So yes, you can use the computer to look at the notes. You don't need to print them out. Okay. We've got like 1,000 pages of notes, not 1,000, but like a couple, a lot, at least over 100, I think. I think some of my lectures are like 60 slides long and stuff. And I guess you can fit like 4 slides on a page or something, but it's too much to print out. So don't print it out. Okay. You can leave it on the computer. That's fine. And you know, it's not, I don't want it to be open internet. I don't know if I can like stop you guys from using the internet. I don't think my questions will be helpful to, I don't think the internet's going to be helpful for looking up answers. Okay. That like I'm aware, like you're going to be logged in on your computer and stuff. And so, you know, no collaboration. So don't try to chat with each other. I know there's like a group chat for the class. Don't use the group chat during the exam. Okay, that's gonna, you'll get in trouble for that. So no collaboration. Don't be sending each other messages. It's open note, open book, and I'm going to tell you basically what you need to practice and study before the day of the exam. So I think that's fair. Okay. Are there questions on just the formatting of how the exam is going to work? And again, this is my first time using Gradescope. I don't know. Have any of you used Gradescope for an exam or something? Okay. All right. And I don't know if you have anything to say about it, but I'm hoping it's fairly straightforward. Okay, in that you I don't know. So we're gonna try this out. Okay, and so try out the practice if especially if you've never used Gradescope, um, to see if it works. Okay, so let me talk about the actual exam questions, and we'll does the exam need to be uploaded by, yes, so the exam must be uploaded by 11:10. So I've written the exam to be done in 50 minutes, okay? So I've written the exam to be done in 50 minutes, like kind of like a regular class time. And then I'm giving you guys like an extra 20 minutes of cushion for the scanning and the uploading, okay? So don't work until like 11:08 a.m. and then try to frantically scan it in the last 2 minutes. And try to squeeze it in there. Yeah, no lecture after the exam. Okay, so don't no lecture after the exam. It's just exam that day. Okay, so make sure you give yourself enough time to scan it and upload it. Okay, you need to get it scanned and uploaded by 11:10 a.m. You want to lecture after the exam? I mean, sorry. I don't know why you would want to lecture after the exam. I guess I'll take it as a compliment, but but yeah, no, just the exam, 10 a.m. to 11:10 a.m. I know that's a little bit earlier for you guys, but that's what we're gonna do. Okay. Okay, so let me talk about the actual content. Okay. All right. Number one, we're gonna be a vector derivatives problem, okay? So I'm gonna give you a function in vector notation, all right? And then you're going to find the gradient of the function with respect to a vector, okay? So, for practice, you can, in the notes, you can look at the ordinary least squares loss function in vector form, and then, and you're gonna see how I take the gradient or the derivative of the loss function with respect to the vector w. Okay, and that's kind of the kind of work that you're going to be expected to do. The problem will not be the ordinary least squares loss function. Okay, it's going to be something a little bit more complex, but you can expect something kind of like that, where I give you a function in vector notation, and you're going to have to take the gradient with respect to a vector there. Okay, it'll be a little bit more complex, right? Because if I give you the OLS, then it's super easy, right? You just find it in the notes and you copy the answers. So, I'm not like trying to make my exam like crazy hard or anything, but obviously it's going to be a little bit more than just find the answer in the notes and copy the answer from the notes. Okay, you got to do a little bit of work and practice. There's a okay. The second question is going to be gradient descent. Okay. Yeah, I will post this document. Okay, I'll post this document. You don't have to frantically write down everything you see on here. Okay, so I'm going to provide some kind of function in 2 dimensions. Okay, and I'm going to provide an arbitrary starting point, location at time t equals 0, and then I'm also going to provide an arbitrary learning rate gamma, and then what you're going to do is you're going to manually do gradient descent. Okay, so you're going to calculate the location at time t equals 1, okay, and then the location at time t equals 2. So so that's what so you'll have to do it manually, right? So obviously you'll need a calculator. Okay, so for the exam you need sheets of paper, a pen or pencil, and a calculator. Okay, to do it. All right, and so you're going to manually do gradient descent. So that's going to be the second question. So I think I've got an example kind of like this in the notes. It's the one where we do OLS and you kind of trace it, and then if it was too big, you end up kind of zigzagging and stuff like that. But I'm going to give you kind of, I guess, some nicely behave values, I hope. That's the plan. All right. Okay. Number 3 will be regularized loss. Okay. And so for this, I'm going to give you a small data set, like a really small data set, like three points or 4 points in 2 dimensions. Okay. And what I will do is I will provide a potential line of fit. Okay. So not necessarily the best fitting line, but given for this, I'm going to give you a potential line of fit. And what you're going to do is you're going to calculate the OLS loss, okay? And then you'll find the I guess not the OLS will be like the squared error loss, and then you're going to find the lasso loss, and you'll find the ridge loss. And for the lasso and the ridge, I'll provide some value of lambda, okay? So I think this problem is probably the easiest one. Okay, number 3. But you know, make sure you can do it. You can try making up some points and try making up a problem yourself. Okay. And then for number 4, the 4th problem will be leave one out, cross validation, and you're going to do this manually. Okay. And then for this one, I'm going to I'm going to provide a small data set, maybe like 3 or 4 data points, and I'm going to have 2 competing models. And what you're going to do is you're going to perform leave one out cross validation for each of these models. Okay, and so the way this is going to work is I'm going to provide lines of fit to n-1 data points. Okay. And so I'm going to provide, for each model, you're going to get n different fit lines, okay? So if I have 4 data points, okay, and I say, I'm going to say, okay, well, what would the line be if I fit the model to points 1, 2, 3? And then I will also give you the line if you fit the model to points 1, 2, 4. I'll give you the model if you fit the line to points 1, 3, 4, and I'll give you the model if you fit the line to points 2, 3, 4. Okay, so you're going to have 4 different lines for that one particular model. Okay, and then you're going to have to find the kind of the mean cross-validation error for those 4 models, and then you would do the same for the competing model, and you would kind of compare the two models between those 2 things. Does that kind of make sense? I don't know if you guys have questions. And then the last page will be some conceptual questions covering kind of material from lecture. All right. And so for these conceptual questions, some of the questions can probably be taken directly from the notes. All right. And then other questions, the answers will require a little bit of thinking. You're gonna have to, they're not gonna be directly from the notes. You're gonna have to think a little bit about why, or what the implication is of some kind of idea. And those will be conceptual questions. And that should be it for this this exam. And I hope it goes okay. So again, I know it's not our normal class time, but you're going to take it either at 10 a.m. or 10 p.m. Okay, so set your calendars, pick one of those times. You don't have to tell me, but you'll log in to Zoom, and I'll kind of take note of everybody who's logged into Zoom, and make sure that you were logged in during the exam time for the kind of the proctoring there. Okay. Any questions or comments or issues? This is all good? We're okay? All right, then, so that's gonna be the plan for Wednesday, and Gradescope's a new thing for me. So I hope it goes well. Okay. When does the covered material end? I would say it will go through week 3 Monday. So Monday's lecture. So on Wednesday I started neural networks. So no neural networks on the exam. Okay. So on Wednesday I started neural networks. I won't put any neural network stuff on the exam. But up through Monday, which has like bias variance stuff, bias variance trade-off, I would say up to there is fair game for the exam. Okay. There will be neural network stuff on the final. Yeah. So we're gonna have a second midterm at some point, and a final, and you can definitely expect neural network stuff to show up in the future. Yeah, but not for midterm 1. Okay, midterm 1 will cover up to week 3 Monday. Do you have to write in pen or can you write with pencil? The answer is it doesn't matter as long as I can see it when you scan it, okay? So if for whatever reason your pen or pencil like doesn't show when you try to like scan the, that's gonna be a problem, okay? So definitely practice using some kind of, practice using a scanner of some kind, whether it's on your phone or a physical scanner or whatever it is, okay? Practice using that. Practice the Gradescope, kind of the practice assignment that I've created on CCLE. It doesn't count for anything as far as your grade goes, but it'll give you practice. It'll give me practice with using Gradescope as well. I don't want there to be technical issues on the day of the exam. So please make sure you kind of practice using the scanner. And you do have to make sure it's scanned and uploaded by 11:10. So don't push your luck too much. I would say give yourself at least 10 minutes for the scanning and the uploading. Okay. Okay. Any other questions there? We're good. Okay, well, yeah, so I'll post this document and we will get started on today's lecture content, okay? So I only got through the first gradient in the first lecture, and so that's gonna be my goal for today, and then we'll, I guess we'll have to finish this up next week, the rest of the gradient descent, okay? All right, so, not gradient descent, back propagation. All right, so I'm going to kind of skip the review quiz, but I asked like, what are the dimensions of your weight 1 and weight 2 matrices and y and whatever, and you can kind of answer that. So on Wednesday, we introduced neural networks, and we talked about forward feed. You take your x's and then your x matrix, which is n by 2, and then you feed that in. You multiply that by your w matrix. The w matrix is 2 by 3. And so you're going to get an n by 3 matrix of z values. You apply an activation function to those z values, and you're going to get an n by 3 matrix called A, which is the values after you apply the activation function. And then you're going to multiply that matrix A times W to get your output values not yet your output value. You're going to get a matrix Z, okay, which is n by 1, because the W's in the second weight matrix will be is 3 by 1. So A, which is n by 3, times the second weight matrix 3 by 1 will result in an n by 1 matrix, and then you apply the activation function there to get your y hats. So these are our weight matrices. Weight matrix 1 is 2 by 3. Weight matrix 2 is 3 by 1. Our activation function right now is the sigmoid function. And this is what it kind of looks like. So we do x times w is z, apply the activation function to f, onto z to get a. A times w is z again, okay, but this is our z in our third layer. We apply f to z in our third layer, and we get y hats. And we can also just write y hat as f of x w1 times w2. Okay, and so what we want to do is we want to train our matrix, or train our neural network, okay? So training our neural network means finding the values in our matrices w1 and w2 so that our loss function is as small as possible, okay? We want to minimize the loss function, and so our loss is going to just be the mean squared error. And if this was just linear regression, y hat is very easy. It's just x times w, right? And we saw how to minimize the loss function if y hat is xw. But in this case, y hat is a little bit more complex. It's f of xw w1 times w2. Okay, and so so I want to minimize the loss with respect to w1 and w2. So I'm going to have to find the gradient of this loss function. And if I find the gradient with respect to w1 and w2, the answer is a little bit too complicated for us to just say, okay, well, let's set the gradient equal to 0 and solve. Okay, it's too complex to set it equal to 0 and solve. So what we're going to do is we're going to use gradient descent. Okay, we're going to find the gradient, and that way we can just start off at some arbitrary starting location and use gradient descent, which will take us downhill and hopefully get us to some kind of local min. Okay. Now, to make it a little bit easier to work with, okay, I'm going to just multiply L by a constant, n over 2, okay, and that's going to give me J. J is equal to 1/2 of the sum of yn minus y hat sub n quantities squared, okay? And then the values of w that will minimize this function J will be the same values that minimize L, because all I did was multiply it by a constant. Okay, so what we're going to do is back propagation. I think I've already talked about this, but we want to find the values of w1 and w2 that minimize that loss function. And we're going to need to solve the gradient so we can use gradient descent. Gradient descent is not guaranteed to give us a local minimum, but it should get us in the right direction. So that's what we're going to do. Okay, so when I take the gradient of J with respect to W1, I'm going to get another matrix with the same dimensions as W1. W1 is a 2×3 matrix, and when I take the gradient of J with respect to W1, the gradient will also be a 2×3 matrix. Okay. When I take the gradient of J with respect to W2, I'm going to get a 3×1 matrix, because W2 is a 3×1 matrix, so the gradient with respect to W2 is also a 3×1 matrix. Okay. And if I had bias terms, like a B1 and a B2, those would also have their own gradients, okay? And I'm not going to do that. That will be in your next homework assignment. You're going to have to find the gradients with respect to the bias terms. Okay, so let's just look at one of these values, okay? Let's say let's look at one predicted value, y hat sub n, and we're going to say, well, what's the, we'll look at them one at a time using the sum. We're going to say, what's the gradient of J with respect to W2 with respect to this? Okay, so here's J. So when I do this, the gradient of a sum is the sum of the gradients. So that's what I have. And so I've got, you know, dW2 of this thing, okay? And so just applying rules of gradients, the 2 comes down and cancels out with the 1/2, and I have to apply chain rule, right? So I say, okay, well, what values in here vary with respect to the second weight matrix W2? Okay, the YNs do not vary, right? The Y sub n's are fixed values. Those are the observed values. The observed values do not vary with respect to our weight matrix. That's the actual value, okay? But our predicted value Y hat, that does vary. Whoops, I don't know what's going on. Our predicted value Y hat does vary with respect to W2. So applying chain rule, I have to multiply it by -1 here, and then I'm going to have to take the derivative, the dy hat, with respect to dW2. I got dy hat dW2, and then I can use chain rule again, okay? And I can say this, okay, well, what is y hat? Well, y hat is found by, you know, we can look at the variable z sub n3, and so we can say, okay, this is going to be equal to dy hat with respect to dz3, and then multiplied by dz3 with respect to dw2. Okay, so we can do this, all right? So if we recall, what is y hat? Well, y hat is the result of taking that kind of final value, z sub n, in the third layer, okay, z sub n in the third layer, and we apply the activation function to it, right? So all we do is we take the activation function, which is our sigmoid function, or our logistic function right here. We apply f to z sub z3, okay, z3 sub n, and that gives us our y hat sub n, okay? And so the derivative of this is just going to be f prime, okay? So the derivative of this with respect to zn, z3, is going to be f prime, okay? So what is the derivative of this logistic function? Okay, well, that's just plain old calculus. And so if you recall your quotient rule, okay, from I think 31a, you know, you got f of u over v, f prime is going to be u prime v minus uv prime over v squared, okay? And so, you know, u is 1, v is 1 over e minus e to the negative t. You solve this and you get e to the minus t over 1 plus e to the minus t quantity squared, okay? So f prime of z3 is going to be this quantity here, right? And this is the derivative of y hat with respect to z3. Okay, so for simplicity, I'm not going to write all of this every single location, okay? I'm going to just plug that in right here, okay? So I've got the derivative of the loss function is this, okay? We have the actual value y sub n minus y hat sub n, f prime of z3 sub n, okay? And then we still have to figure out how z3 varies with respect to w2. All right, is this all okay? Have I lost anybody? Are we doing okay here? We're doing okay? All right, okay. Well, thank you for your check mark. All right. All right, so this is where we are. And now what we want to do is we want to find how z varies with respect to the second weight matrix, okay? How does z3 vary with respect to the second weight matrix? Okay, so we want, so if we think of the entire matrix z, okay, the entire third matrix z, entire matrix z in the third layer, that is going to be n by 1. We've got n observations, and z is going to be the matrix of kind of the results of all of those things. So we've got n by 1 observations, right? And prior to this, we have to say, well, okay, how did we even get z in this first place? Okay, so if you think of, so we're on slide 19. So if we go back to this, remember to go from, we had to take the activated values, multiply it by our second weight matrix to get z, right? So this is, so to get this matrix z3, we took our activated values in the second matrix and multiplied it by w2 to get that, okay? So this is where we are, okay? And so that matrix of activated values in the second layer, where it was has dimensions n by 3, and w has dimensions 3 by 1. Okay. All right. If we look at just one value, z sub n, okay, z sub n is a scalar value. All right. And we would look at just one row in A, and that would be a 1 by 3 kind of row matrix. And we would multiply that by the matrix of W, weights, and that's going to be 3 by 1. Okay, so the question is, well, what would be the gradient of this value of z sub n with respect to W2? All right, so if you guys recall, I think back in lecture week 1, maybe our second lecture in week 1, I showed you kind of the rules of taking gradients, okay, with respect to it. And so if you have basically a vector times a vector, the gradient of this with respect to W is going to be, you know, whatever I'm multiplying over here, transpose, okay? So the gradient of this with respect to this is going to be A sub n transpose, right? So the derivative of this with respect to W2, okay, is going to be this thing transpose, so that we're going to have the same dimensions, right? So remember, this has to have be 3 by 1, and we're going to have this 3 by 1. All right. Okay, so if I bring that here, okay, the derivative of z3 sub n with respect to W2 is going to be A2 sub n transpose, okay? This is what I have, all right? And so far, this is okay, all right? The derivative of J with respect to W2 needs to be a 3 by 1 matrix, okay? Because W2 has dimensions 3 by 1. And so the derivative or the gradient needs to also have dimensions 3 by 1. And this works out because right now we've got a scalar, okay? Y sub n, that's a scalar value, minus y sub n scalar value. So this is a scalar multiplied by f prime of z sub n, that's a scalar. So I've got a scalar value 1 by 1 times this matrix, which is 3 by 1. And so this quantity is 3 by 1. And then I sum them up across all of the different ends, okay? And so what we want to do now is we want to somehow be able to take care of this summation function, and we're hoping we can take advantage of kind of the matrix multiplication, those operations. Is there a way I can do this, okay? So one thing we can do is we can say, well, what if I got rid of the subscripts? What if I got the subscripts n, and I just left them in their vector matrix form, okay? If I do that, okay, because these are the right elements, so this is correct so far. If I do that with y, this y sub n becomes the matrix y, and y hat sub n becomes the matrix y. And so these are going to be matrices of dimensions n by 1. Okay? And if I do that with the matrix Z3, okay, Z3 sub n is going to become the matrix Z3, which will also be a matrix of that's n by 1, right? You know, applied to f prime. So I've got f prime of Z3. This is also an n by 1 matrix. And then if I do this to A2 transpose, okay, A2 sub n transpose, and I get rid of the n here, this is going to end up being a 3 by n matrix, okay? So A2 transpose will be 3 by n. And so far, you know, these are the correct elements that I've got to multiply, but I can't multiply them like this. The dimensions don't line up. If I try to do matrix multiplication, this times this times this, I'm going to get a mismatch error. I've got an n by 1 times an n by 1, which, you know, I can't do regular matrix multiplication there. And then I'm trying to multiply that by a 3 by n. I can't do matrix multiplication there either. Okay, we're going to get some kind of dimension mismatch. So what I need to do is I've got to take these terms and I have to rearrange them, all right? So I'm going to take my A2 transpose and I'm gonna push it to the front, okay? I'm gonna bring this around to the front, okay? and that will line up our 3 by n's, 3 by n by n by 1. That's going to line up correctly. And then I'm going to, for these two elements, I'm going to perform element-wise multiplication, okay? So normally you can't do an n by 1 times an n by 1. But what I'm going to do is I'm going to say I'm going to multiply these together using element-wise multiplication. So you can imagine I've got a column of n values right here for y minus y hat. And I've got another column of n values for z, z3. And I'm going to go element-wise. I'm going to multiply each of these things. And the first element times the first element, second element times the second element, third element times the third element, so on and so forth. I'm going to go down the line. Okay. And so, so this quantity is going to be y minus y hat element-wise multiplied by f prime of z3. And so this, when we multiply, will result in an n by 1 matrix here. Okay. And so that's what we have here, right? Okay, and so I've got dj, dw2 results in this, okay? And this multiplies out to be a 3 by 1 matrix, okay? Which is exactly what I want, okay? I want the gradient of j with respect to w2 to be a 3 by 1 matrix. Now, I'm following kind of the Welch Labs video does, okay? And he calls this quantity y minus y hat element-wise multiplied by f prime of z3. He calls that quantity delta 3, okay? So we're going to have A2 transpose delta 3, and this results in a 3 by 1 matrix, which is exactly what we want here, okay? All right, how does this feel? Does this feel okay? Questions? Got some thumbs up. Oh, you know, I forgot to give you guys, let me give you the quiz answers for today. Quiz answers for today is A as an apple for the first question. First question is A as an apple, and second question is E as an elephant. A as an apple, E as an elephant. First question is A as an apple, second question is E as an elephant. Okay. This is where I got as far as I got in the first lecture, and so what we want to do next is we want to take the gradient with respect to the first weight matrix. Okay, so this is the gradient with respect to the second weight matrix. Okay, and then we're going to have to keep working backwards, and so this series process is called back propagation. We're going to have to find the gradient with respect to the first weight matrix. Okay. But I'll save this till Monday, okay? So, so we might end just a couple minutes early today, just so that the two lectures I kind of have at the same spot. So on Monday, we'll pick up looking at the gradient with respect to the first weight matrix. I've got way too many slides here, but I'll just use these same notes in Monday's lecture. You can go ahead and look ahead and try to familiarize yourself with some of the terms here. But basically, a whole bunch of matrix notation in terms of taking derivatives and gradients here. Okay, we'll end here for today. And so please be sure you try the practice grade scope assignment on CCLE. And submit that so that you'll have no surprises on the day of the actual exam next Wednesday. All right. So we'll see you guys on Monday. Have a good weekend. Stay safe. Stay healthy out there. And we'll see you soon.